Hello everyone. In today's lecture, we'll discuss decimation in time. It is one of the class of FFT, right? Fast Fourier transform. All right. So before moving to decimation in time, we must know some properties of Twiddle factor because decimation time or FFT, if we say, it actually exploits the properties of Twiddle factor, right? So a Twiddle factor actually follows periodicity property, symmetry property, and obviously the radix relation. Periodicity property says that if k is shifted by n units on a circle, then the Twiddle factor, the value of Twiddle factor will repeat itself, right, at every n distance. Okay. Likewise, symmetry property states that if k is shifted by half the length of the sequence, right, that is n by 2, then we'll have same value of Twiddle factor, just a minus sign will come in the front, right? According to third property, if your Twiddle factor is squared, right, so that square will reflect in its radix, right, that this becomes n by 2. Okay, and this radix may vary like n by 4, n by 6, that depends on the power of Twiddle factor in this place. Okay, now there can be different types of FFTs, DIT FFTs, like radix 2, radix 4. Okay, that depends on this radix base, where we represent this n, that is number of output points, right, that can be represented as power of 2. Okay, where m is any integer value. All right, this m actually decides the number of stages in butterfly diagram of FFT. All right, but that will see later words. All right, now for understanding of DIT, let us consider a sequence xn, that is an endpoint sequence. Okay, and here we decimate or break this sequence in two equal parts, right? So n divided by 2, this will be one part and this will be another part. Let's say this is even indexed values and this is odd indexed values. All right, now one question might be coming to your mind, right? Why we are decimating this endpoint sequence? See, for that you need to understand that the whole idea of FFT is based on the calculating small sequence DFTs and then add them all. All right. In this particular example, we've divided this sequence into two equal parts. Right. It can be four equal parts. Right. So this will become n by 4, n by 4. Right. Likewise, this will become n by 4 and n by 4, and this chain may carry on. So unlike DFT, we'll calculate DFT for n by 2 sequence for this particular case, and for even indexed values, and then DFT for n by 2 for odd indexed values. Okay, and then add the two results to get final x of k value, the final DFT value. All right, so let us represent the even indexed values with this notation x of en, right, that is even sequence, and this can be further written as even multiple of n, right. Likewise, for odd sequence we can write x 2n plus 1. All right, and obviously their length will be, initially it was for endpoint DFT, it was from 0 to n minus 1, right. The total length was n, correct. But for because we have decimated these sequences equally, so this time my n will range from 0, 1 and up to n by 2 minus 1. All right, likewise for odd sequences it will range from 0 to n minus 2 minus 1. All right, we know that endpoint DFT of sequence xn can be represented with xk equals summation n equals 0 to n minus 1. All right, xn Twiddle factor, multiply with Twiddle factor to the power nk. All right, where k ranges from 0 to n minus 1. All right, the length of the sequence is n. Okay, now let us separate even and odd parts of this sequence so that my xk will become equal to summation n will range from 0 to n by 2 minus 1. Alright, half of the length of the sequence n. Alright, so this I'll write xen. Actually, I'm decimating this thing in even and odd parts. Multiply with Twiddle factor plus summation n equal to 0. Sorry, I'll replace this n with 2n. Alright, because this is even part. So for odd, it will become Twiddle factor to the power 2n plus 1 multiply k. Okay, so this is for even part and this is for odd part. Alright, so let us solve this further. So xk will become equal to summation n equal to 0 to n by 2 minus 1 xen Twiddle factor to the power 2nk plus, see, Twiddle factor to the power k I'll be taking outside the summation. Alright, so Twiddle factor to the power k I'll take outside summation, then summation n equal to 0 to n by 2 minus 1. Sorry, I missed this here. X naught n Twiddle factor to the power 2n k. Alright, now we know that Twiddle factor wn is equal to exponential of minus iota 2 pi by n. Alright, if I square this Twiddle factor, right, so this exponent factor will also get squared. Alright, or we can write this like this also. Okay, now if I take this 2 in the denominator part, so this will become n by 2. Alright, in the denominator it will become n by 2. Okay, now if you compare this and this part, so these are quite similar. Only difference is that here you have n and here you have n by 2, right? So if this is equal to wn, right, with radix n, so this I can write as w n by 2 with radix n by 2. Alright, and that is one of the properties of Twiddle factor, right, radix relationship, which we were discussing in the starting. So we can replace this wn to the power square to the power 2 with this thing, right, w radix n by 2. Okay, in here and at this place. Okay, so let us rewrite the equation. The xk will become equal to xk equals summation n equal to 0 to n by 2 minus 1. All right, xen. Okay, and I'll write wn by 2 to the power nk. All right, I've substituted for this thing. Okay, plus wnk, that was in front, summation n equal to 0 to n by 2 minus 1 x naught n w n by 2 nk. All right, if you carefully observe these equations, these are nothing but the DFTs, right? This is DFT for this one is DFT for even sequence and this is DFT for odd sequence. So I can write it ek. Will it be correct? Right, this I can write like x naught k. All right, therefore my xk will become equal to xek, right? Let's replace this with xek plus this Twiddle factor will remain as it is, multiply with x naught k. All right, let us mark this equation number 1. Okay, now I get the idea that once the individual DFTs are calculated, right, for n by 2 sequences, n by 2 length sequence, right, then they are combined as per equation number 1. All right, so this was the equation when k was ranging from 0 to n by 2. All right, now the next case is when k is from k is greater than or equal to n by 2. All right, so let us consider this property. This is known as symmetry property. All right, wn to the power k plus n by 2 equals minus of wn to the power k. All right, now let us consider a line. All right, this will range from 0 to n. Now if I divide it equally, so this point will be n by 2 exactly. So last equation I was calculating from 0 to n by 2, right, but this time k is greater than n by 2. All right, so if I have to do the calculation for this part, I'll write it k minus n by 2. All right, this will give me this segment. Okay, so let us substitute this k minus n by 2 in place of k in this equation. All right, so this will become equal to wn to the power k minus n by 2 plus n by 2, all right, equal to minus wn k minus n by 2. Okay, so this n by 2 cancel outs. Ultimately, we are left with wn to the power k equals minus wn to the power k minus n by 2. Okay, so let us substitute value of Twiddle factor in equation number 1. Okay, so this term will get replaced with this thing. All right, this term will get replaced with minus of Twiddle factor. All right, and replace all the k with k minus n by 2 in this equation. So let us rewrite this equation. X of k will now become equal to x e even, right, k minus n by 2. All right, minus, in place of this I'll write this. Okay, so negative sign will come in front, wn k minus n by 2. Okay, x naught k minus n by 2. All right, mark this equation number 2. Now for equation number 1, my k was ranging from 0 to n by 2. All right, but this time it will start from n by 2. All right, and range up to n. All right, minus 1. Now let us consider an example. Right, let n be equal to 8. Then xek will be 4 point DFT. Okay, and x naught k will also be 4 point DFT, that is n by 2 point DFT. All right, now for n equal to 8 we'll have 8 samples. All right, so I can write my sequence like this: x0, x1, x2, x3, x4, x5, x6 and x7. All right, now if I have to decimate this sequence into two parts, I mean two equal parts, that is n by 2. Okay, so let's separate out even samples first: x2, x4 and x6. All right, and another ones are the odd samples: x1, x3, x5 and x7. All right, this is my even sequence, right? Likewise, this is odd sequence and its length is n by 2, that is equal to 4. All right, likewise this is n by 2, that is equal to 4. Okay, now as we are studying DIT, all right, decimation in time. Okay, so obviously one sample will be decimated in between two and will pair alternate samples. Okay, like x0 will get paired with x4. All right, likewise x2 will get paired with x6. Okay, so in between x0 and x4 we've skipped x2. Okay, so that is decimation. Okay, likewise for odd, x1 will get paired with x5, likewise x3 will get paired with x7. Okay, so every time you have to pair with alternate samples. All right, so every time you pair two samples, they will result in two separate equations. Okay, one comes from equation number 1 and another one is just like equation number 2. Okay, so there will be two different cases. One is for k from 0 to n by 2, right, and another one is for n by 2 to sorry, this is for 0 to n by 2 minus 1. All right, and second case is from n by 2 to n minus 1, right, that is 7 here. All right, so general equation for this one will be xk, the DFT of this thing will be xk xek, right, plus w, what is the value of n here? 8. All right, to the power k x ok. Okay, this is coming from equation number 1. All right, in similar way, from equation number 2 we'll have xk equals x e k minus k minus n by 2, right? So n by 2 for this particular example is 4. All right, minus w8 to the power k and x naught k minus n by 2 again, that is 4. Okay, now let us calculate xk for different values of k, right? So let's see for equation number 1 first. X 0, let's substitute k equal to 0. It can take 4 values, 0, 1, 2 and 3. All right, so let's do for k equal to 0. So x0 will be, just replace k with 0. All right, plus w8 to the power 0. Okay, x0 0. All right, that is the first one. Then for x1 it will be xe1, right, plus w8 to the power 1 x o1. All right, o means odd, right? Then x2 will become equal to xe2 plus w8 to the power 2 x naught 2. All right, then x3 equals xe3 plus w8 to the power 3 x naught 3. Okay, now let us calculate for equation number 2. Okay, that is k can take values from 4 to 7. All right, and we need to substitute these values in this equation. So xk, this time I'll replace k with 4. All right, the first value is 4. Okay, so this becomes equal to xe. Now 4 minus 4 will be 0. Okay, minus w8 to the power, this is also k minus 1, sorry, k minus n by 2, right, k minus 4. So this will also become equal to 0. All right, x naught 0. Okay, now what about the next value, that is x5. All right, so let's see xe. See, xe 5 minus 4 is 1. So this will become equal to 1 minus w8 to the power 1 x naught 1. All right, likewise for x6, it is xe2, right, 6 minus 4 is 2 minus w8 to the power 2 x naught 2. All right, likewise for x7, it is xe3 minus w8 to the power 3 x naught 3. All right, this information is helpful in drawing of butterfly diagram or flow graph. All right, now if you observe carefully, these are basically the DFTs. All right, these are the outputs. Okay, so this output and this output are having same input values. All right, we are multiplying this Twiddle factor with this x naught, x o naught, right, and adding the result with x e naught. Likewise, here we are multiplying this same Twiddle factor with x naught 0 and subtracting this from x e naught, right. Likewise, if you see, there are similarities between x1 and x5. Okay, output x2 and x6, likewise x3 and x7. Okay, so all these pairs have same input values. All right, so this operation can be represented with the help of butterfly diagram, right. See, here's one, right. Now our inputs were for first equation. Let's see, the inputs are x e naught and x naught naught, right, x o naught, multiplying with this Twiddle factor. All right, now see, the inputs are x e naught and x o naught, right. Okay, the things will get multiplied on these straight lines, right, and on these cross lines at this at actually these on these nodes, your values will get added up. Okay, now if you see, this x e naught will get multiplied with this one, and ultimately it results x e naught at this place. Okay, now this xo0 will get multiplied with this Twiddle factor and will get added up with this xe0, right? And results x0. Okay, all right. Likewise, if you see this side, this x0 naught, xo naught, x naught 0 will get multiplied with -1, right? And Twiddle factor w80. Okay, so we'll get this term, all right, and we'll add minus of this thing with xe0 coming from this side, all right. So that is nothing but the x4 if you can observe it carefully, right? So here from here again we can conclude that this x0 can pair with x4, likewise x1 can pair with x5, okay, x2 can pair with x6, and x3 can pair with x7. So let us consider the even samples first. So x0 and x4 will get paired, likewise x2 and x6 will get paired. So let's see a detailed butterfly diagram. You can see in here x0 and x4 are getting paired, right? This is one butterfly diagram. Then x2 and x4 they are getting paired, likewise 1 and 5 they are getting paired, and 3 and 7 they are getting paired, and there will be three different stages, all right, three different stages of this butterflies. Actually we have this thing 2 to the power m, right? That is equal to n. Okay, for this particular butterfly diagram we know n equals 8. Okay, so 8 will be equal to 2 to the power m. So from here we get m equal to 3, right? So this clearly indicates that we'll have three different stages of butterflies, 1, 2 and 3, all right. Likewise, if value of n increases, definitely my number of this butterfly calculations will also increase, computations will also increase, all right. So we'll discuss them in detail while we'll discuss the problems. All right, that is all for now. Thank you very much.